So you can see the screen, right, where the week numbers are given.
Yes.
Okay. Fine. So this week we will be dealing with some of the basic concepts that were covered in the lectures for this week. And I suppose because I don't have the access to the NPTEL portal nowadays, so for solving those problems, I will just give example of some analogous problems or similar problems, and we will deal with that. So have you seen the assignment for this week? How do you feel about the problems this week? Questions, I mean. Are they, I mean, tough, easy, or you can mention the level of the questions this week so that we can go through that pace depending on that. Or you have not looked at that. It might also be possible. Anyways, I think it's fine. Okay. And yeah, I mean, and please just ask for any doubt, any queries uh, for if you don't understand anything. If it is okay, I mean, I can also explain in other languages, let's say for Hindi example, if you have really doubts. So don't please hesitate about that, okay? So that is not a big deal. Let me just go through the slides. Okay, so okay, fine. So you can see the Atlantic Meridional Overturning Circulation, right? AMOC, AMOC. Okay. So this was a major part in the lectures for this week because it is a very vast current, ocean current system that prevails in the Atlantic Ocean. And in that AMOC, it is actually part of a global thermohaline circulation that carries water throughout the oceans of our world because our oceans are actually connected. Uh, uh, of course, our land is only a small portion of the surface. Only, I think, 30% is the land and rest is ocean. So oceans are also connected. And the main importance of this meridional overturning circulation, or let's say the thermohaline circulation. So forget about all the details. Can you just tell what is the main purpose or main requirement, or let's say main importance of this circulation in terms of basic physics, what it does? Forget about the details where it flows, what are the regions, but the main purpose of this circulation or any circulation, be it atmospheric or oceanic.
Transports heat from tropics to the poles.
Okay, and why it is required? Why transporting of heat is required?
So energy balance. I
Okay,
mean, like so. Basically, in the latitude and the lat at the equator to 30 degrees south to 30-degree north,
okay,
the amount of absorbed heat is uh, greater than the amount of emitted heat.
okay,
But for higher latitudes, so the amount of absorbed heat is less than.
okay. So what would happen if these circulations were not there? So if the
If there
circulations
won't
are
be an
not there,
equilibrium, there
then
won't be equilibrium. It will the temperature will not be maintained. Like
I
okay,
mean,
I'm not sure.
there should be an equilibrium. There, I mean, of course, we will get an equilibrium, but that would have very high contrast of the temperatures between the pole and the equator. The equatorial region will be much hotter, and the polar regions will be much colder. The disbalances would be there.
Okay,
So
okay.
basically, we're experiencing or we are absorbing the constant amount of energy, almost constant. Forget about the climate change or global warming for the time being, but that energy is distributed or redistributed through those circulations. Now, if the circulations were not there, then I would say there will be more. drastic, there will be more drastic changes in the temperatures. So maybe the polar regions would experience a lot more colder environment, and the equators will be a lot more hotter like that. So the main purpose is, or basically there's a physical nature, there should be something to transform the heat until the point where there is a temperature gradient, or gradient of, if you know about diffusion or the physical processes of any variable that can
Okay.
actually interact to balance the particular scalar. Here it is temperature or salinity, those type of things. Okay. For atmosphere, it is the temperature and moisture. For ocean, it is temperature and salinity.
Will be changed.
Because due to those things, there will be a flow of circulation or ocean or atmosphere, I mean water or air, whatever it is. Okay, fine. Okay, that is the main purpose, of course, that is the basic physics. So now, if we go to the details, we will see that due to the winds, mainly the trade winds or the westerlies in the higher latitudes, the flow will be from the surface level, that will go towards the North Pole or Atlantic uh, meridional ocean circulation. So after going to the North Pole, it will face some barrier, and also it will sink because the Atlantic water is not very fresh. It contains a lot of salinity, and if it goes towards the North Pole, it will experience decrease in the temperature, and of course it is already saline, so saline water is denser than the fresh water, so it will drown towards the North Pole. And if it sinks, then there has to be something to balance that. It cannot just accumulate over the North Pole. So the returning force, suppose you heat a wall, then you have to come back, or let's say water heats a wall, then it should come back, it cannot penetrate the wall. So that forms the North Atlantic deep water, that will go in the opposite direction, that is from north to south, but the changes are that it is highly saline and it is very much lower in the temperature, so it will flow towards the bottom side of the Atlantic, and it will travel throughout the Atlantic Ocean towards the South Polar Southern Ocean. And it is high in salinity and high in dissolved oxygen and nutrients also. Can you tell me why it is why colder water are high in dissolved oxygen as well as in dissolved nutrients? Ankit, Mukesh, you want to say something? So the question is why colder water contains more nutrients or more dissolved oxygen. That is important in biogeochemistry actually, because if there is upwelling or water is going from bottom to top, then always there will be an increase in the nutrients in the region, increase of oxygen in the region, and there will be bloom of the different species, let's say phytoplankton, zooplankton, those type of species. But why it contains more oxygen or more nutrients? Any idea? Okay. So the thing is, the solubility of gases in colder water is more than the solubility of gases in warmer water. So that is the case. And if you heat up water, the amount of dissolved any type of gas will increase. If you decrease the temperature, it will increase, and if you increase the temperature, it will be decreased. So the solubility of gases generally decreases with increase in temperature. That the opposite thing happens when you try to I mean, dissolve a salt or any type of solid substance. That's why um, if you cool a water, then if you add some salt or sugar, for example, you might see some sugars or salts are left behind. Okay, so that is the difference between solid and gas in terms of solubility in the water. So it's basically coming from chemistry. Okay. I mean, that is so you just need to remember that if the water is cold, then it will be high in dissolved oxygen and nutrients. And somewhere, if the cold water comes towards the surface, it will increase the amount of nutrients, increase the amount of oxygen in that region. So there would be, of course, if there are species different living beings, they will be attracted towards that place and they will start breeding and they will increase in numbers. That's why they will you can see a bloom in the uh, I would say phytoplankton, zooplankton, other species that live in the ocean or sea. Okay. Anyways, so after reaching the southern ocean, it will actually go to the south pole, and then it will be distributed towards different parts, Pacific, Atlantic, or even South Indian Oceans, and that's how these are connected. And in the Pacific Oceans, they will be again driven by winds. They will come towards the Antarctic region or Southern Ocean region, and they will be actually distributed. That's how the circulation works. But the prominent circulation is towards the Atlantic. That's why AMOC, Atlantic Meridional Overturning Circulation, is very important. Also, there are very important land masses towards the two sides of the Atlantic Meridional Overturning Circulation. Atlantic Ocean is not a very big ocean, so it affects both land masses. One is the American, USA, or Canada, this type of region, also Greenland, and another is the European part, the Scandinavian region, let's say Western Europe, this type of regions. Okay, and okay, so we will come to that about the salinity, but the Atlantic water is more salty because there is disbalance between or imbalance between those. Evaporation and precipitation. So evaporation is more and precipitation is less. As a result, the salinity will go down. Sorry, the salinity will increase, or the fresh water will be actually extracted from that region. That's why the salinity will increase. Okay. There is a picture of the thermohaline circulation, and this region is what we call as Atlantic Meridional Ocean circulation. So these are driven by winds, and it is a very famous stream called Gulf Stream. And from that, it will be affected by the westerlies, and it will go towards the North Pole. And as it is already high in salinity, it is relatively dense compared to the fresh water. And here at this region, it will also release the heat. Because of releasing of the heat, it will sink at this region, but there's boundary, so uh, it has to come back, and there will be very cold areas near this point, and also icebergs will be there. So that released heat released will bring the temperature down, and it will start coming towards the south pole, and here it will join the southern ocean circulation, and the southern ocean circulation will be actually divided into multiple parts. One will go to Indian Ocean, another will go to Pacific Ocean. This will again be driven by the winds because there is strong trade wind here that pushes the water, surface water here from this is called maritime continent, so this region, and from there it is again distributed into Atlantic Ocean or Southern Ocean, and yeah, that's how the thermohaline circulation works. So there is a very important circulation in controlling the temperature or the climate of the whole globe. And it is seen that due to multiple instances of strengthening or weakening of this Atlantic Meridional Ocean circulations, the temperatures of, I mean, the regions which lie between the path of the circulation were heavily affected. That's how the colder or warmer periods occurred in the past, evident from the paleoclimate data. Okay. Okay. So, any question on this thermohaline circulation? You can please ask. I will try to answer.
Why is heat released into the air, yeah, in the deep water section in the north?
Oh,
Yeah.
okay, okay. No, I mean, it is actually. here also it is slowly becoming from surface to deep. So this whole region is very cold. That's why the temperature of the atmosphere is less than the temperature. I mean, the atmosphere will be less than let's say 0 degrees Celsius, especially. I mean, most of the time of the year, but the water uh, will not go to temperatures below 0 degrees Celsius. So there will be always chances for heat releasing throughout this region, unless and until it sinks. After sinking, it cannot release the heat because it will go down. But before sinking, this type of heat releasing will prevail. After sinking, it cannot, of course, go. I mean, it cannot release the heat because it is surrounded by water, then not air. That's the reason. Similar case for the southern ocean also. So heat released into air, there must be air, so the water will be at the surface, and these regions are minus in negative temperature. So these are always below zero. You know that average temperature of Antarctic region or average temperature of the Arctic regions.
So will
So
ice be formed over there or?
ice also forms over there. Yes, yes. And there is annual cycle, not annual, there is seasonal cycle of ice. So if you plot the extent of ice here, it will start increasing or decreasing. So the ice cap, the extent of the ice cap will vary according to the season. I think there's a seasonality of the ice cap in the ice cap season, ice cap which season in Arctic, let's say, I don't know. So there is a Yeah, I mean there of course there is a ice cap here. So there is ice cap here, but it changes with respect to time. Very quickly. Yeah. So it also depends on the season. During winter it increases, the extent increases. During summer it decreases. They are just showing for 1 year that during summer it will be reduced, but also if you just focus on August, it is less, and if you focus on uh, January, let's say May is also fine. It is more in this region. That's why uh, the Arctic ice cap is there. And also, scientists have predicted that the ice cap will somehow be completely melted in 2030 for the summer months or so. So that is a warning for global for the climate change. Okay.
Okay.
Yeah, when it encounters with ice, then also it has to reduce its temperature because the ice there will be colder. I mean, there is latent heat difference in the water and ice, so it will also release some heat there. Okay, so as some of you were suggesting some questions. Okay, okay. So I think last class you asked about the questions, right? So what questions you should practice or what type of things you should uh, uh, do for better performance of this course. So I asked this. I don't know. Nikita asked this or Anant Mukesh asked this. I forgot. But uh, I don't. Can you confirm, Nikita, whether you asked this question?
Yes, sir.
Yeah, you asked about the practice questions or something like that will be helpful in exam also.
यस सर मैंने किए थे आपसे क्वेश्चन वो
Right, right, right. So the thing is, I think the instructors told me that you are getting some assignment questions, right? So the assignment questions might be little out of the syllabus. Do you feel like that or not?
ओके सर
So you don't need to follow the assignment questions. So just follow the lectures and all the questions will come from the lectures in the examination. So if you take the parts of the lecture and if you just practice questions from that content of the lecture, it will be sufficient. But I will also try to provide some questions based on uh, my understanding that is contained within the lecture. So you can also follow this. But there is no specific book that the professor is following to make questions. So, and it will not be out of the box. That is the information I got. Okay.
Okay, sir. Thank you.
Okay. You understood, right? Or shall I tell in Hindi or something?
Yes, sir.
Okay. So आप पढ़ाई कीजिए जो सर लेक्चर में दे रहे हो उसके अंदर से सवाल आएंगे पर आपको बाहर से ज्यादा कुछ करने का जरूरत है नहीं तो अध्ययन कीजिए अच्छे से ये जब सब दी है उससे ही बात बन जाएगी और मैं भी जो करवा रहा हूँ वो भी थोड़ा देख लीजिए उससे हो जाएगा ऐसा होने का जो सवाल है वो थोड़ा मुश्किल लग सकता है तो ऐसा अगर सवाल लेक्चर्स के बाहर से आए वैसे सवाल नहीं आएंगे इसमें ओके
Yes, sir.
ओके सो नाउ I will uh, like to have some interactive session with these questions. So, for thermohaline circulation or AMOC, can you mention two factors which determine the strength of AMOC? Okay, the actual answer is written here, but can you explain? Can you tell the answer again and explain the two factors which determine the strength of AMOC?
So as temperature difference and salinity gradient increases,
Okay.
uh, there will be more density differences that will drive the flow. So higher the density differences, higher the strength of the flow.
Okay, so both temperature and salinity would change the density of the water, and if somehow the density of the water is different, so of course there would be flow in order to balance the density because dense water cannot lie on top of light
uh,
water, right? It has to go down.
Go down.
Okay. So uh, you everyone else understood or shall I explain again?
Oh, it's fine.
Okay. I'm just asking the other. Navya Thomas. Navya is not here. Okay, fine. Nikita, you understood the concept, right?
Yes, sir. I understood.
Okay, thank you. The second question is mention the major factor that controls the Gulf current and the Kuroshio current. So, okay, I will ask this question to Nikita. Can you answer the question?
Yes, sir.
Please answer this question. Mention the factor that controls the Gulf current and the Kuroshio current. You know about those currents, right?
Sorry,
Gu-
sir.
Gulf current, which is towards the coast of Mexico and United States of America, and Kuroshio current that is towards the coast of Taiwan, Japan, these areas. So, what is the factor that controls these two ocean currents? So, yeah, so the answer is also written here. Can you tell why it is controlled by wind? Some comment is there.
There will be
Okay. Sir, I'm traveling. Navya Thomas. Okay, it's fine. No problem. You can type if you want anything. Sorry, Arjun told me.
yeah. So I think there'll be shear stress, right, due to wind.
Right, I
So
mean, yes, yes. So there will be shear stress because they are shallow currents. So due to wind, they will uh, at the boundary between wind and ocean. The wind and ocean, they will have some. That is a concept of viscosity, right? So it will try to take the topmost layer of ocean along with it, and alongside it will be there is some bulk aerodynamic formula for this type of things. And, that's how they control. But the wind is prevailing, so alongside the water will also go, and it will not be it will not be limited to exactly the surface, but it will also extend up to few meters or few hundred meters. That's how these flows these flows prevail. So there are two parts in the thermohaline circulation. One is the surface current due to winds, mainly due to winds. Another is the, as you told, temperature and salinity. They are based on buoyancy, so or the density difference, as you mentioned. These two
The
factors.
Archimedes principle.
Right.
No, buoyancy is it determined by Archimedes?
Yes, yes, basically, yeah, yeah, yeah. They are same. These are just, I mean, different names, but the main concept is the same. So the
Okay.
dense thing must come down.
Okay.
It's the concept. Okay, let's go to the. Okay, the thing, the next question we have actually answered. Why does the Atlantic meridional circulation sink and pond the North Atlantic deep water? Because it is already saline, the Atlantic water, due to less precipitation and more evaporation. It is already saline, and it loses the heat due to the release of heat into the cool or colder atmosphere. Okay, so these are the two factors that control the sinking and as well as the formation of the Atlantic deep water. This is a very informative question. I am not very strict about this type of questions or not very willing to ask this type of questions, but sometimes it might come into your questions that what are the values. So flow rates of AMOC and Gulf Stream. So for AMOC, it is 17 sweat drops. If you measure it at, let's say, 28 degrees north into the Atlantic Ocean, and the Gulf Stream is a much stronger stream and it transports 100 sweat drops. So sweat drop, are you familiar about the unit sweat drop, or I shall explain it?
No, I don't. We don't know. I don't know. Can you
You don't
explain?
know?
What's the concept? I don't know.
Okay, okay, okay. Sweat drop. A sweat drop is basically volumetric flow. As a mentioned, one sweat drop is 10 to the power 6 meter cube per second. So meter cube is the unit of volume, right? Centimeter cube, meter cube, also liter. These are units of volume, and that is flowing per second. So let's say you have an area and you have a through that area you are so you have an area, let's say some cross section, and throughout that area some flow is coming or going. So there are transports of liquids or fluids throughout this area, and what is the rate in which the fluids are flowing. So in order to determine the rate, you have to take one unit time, and in that particular unit time, let's say 1 second, how much flow is made, how much volume has passed through that cross section. That is the amount, volumetric flow or volume traveled per second, volume traveled per unit time. That is the concept of volumetric flow. Now, sweat drop is defined as 10 to the power 6 meter cubes per second. So it means that if you have a uh, volume of 10 to the power 6 meter cube, 10 to the power 6 meter cube means, I think, let's say cube of 10 meter, right? 10 to the power 10, sorry, 100 meters. So 100 cube is 10 to the power 6. So that much amount of volume is flowing per second. It is a very large unit and it is successfully used in ocean measurements because the values are mostly uh, lied between this sweat drop range, or you can you take 1 to 200 sweat drops, you can mostly quantify conveniently.
Flow rate actually changes latitude.
What?
Flow rate, does the flow rate change that latitude?
Flow rates change with latitude. Yes, flow rates also change with latitude. That's why for the continuity equation, the flow coming is equal to flow going,
Range.
but the area at different latitudes and the depth of the currents of different latitudes are not the same. So the
Okay.
flow might get shallowed, it might get deepened, it might be compressed, it might be extended, but the total volume should be constant. But volume is just the and volume is area times the length, right? So if these
Okay.
dimensions change, then the flow will also change. So, but the total I mean, incoming and outgoing, if you take the all volume, then it should be a constant because otherwise there will be accumulation of water, right? So that's how we
but not
define for different depths. For bottom, we define something else. For top, we define something else. That's how it works.
okay. Thank you.
Yeah, actually, I think if you just sum the North Atlantic deep water and Atlantic Meridional ocean circulation, the top part, then both should cancel out and come to zero. But there will be variations across different latitudes and longitudes. That is the concept. Okay. Bipolar seesaw in the context of it. Okay. So if you consider this meridional circulation, you can see that the hot water is being relatively hot water is transported towards the polar region and colder water is transported towards the south pole region. So if this circulation is weak, then less heat will reach the northern region and more heat will be trapped in the southern region. So there will be decrease in temperature in the northern region, but increase in temperature over the southern region. Similarly, if this circulation is strengthened, then it will transport more heat into the northern hemisphere and less, it will trap less heat in the southern hemisphere. That's why the circulation will increase the temperature in the northern region, northern hemisphere, and decrease the temperature in the southern region. That's why there is a opposite sign between there are opposite signs between temperatures for the north and the south. I mean, temperature anomalies, not exactly temperatures. That's why it is called a seesaw. So temperature anomalies in north and south poles show opposite signs. That's how the bipolar seesaw is defined due to the transport of heat and due to the temperature, opposite signs of temperature in these two regions. I will ask for any doubts for this seesaw. Any doubt for this seesaw or the opposite phases of temperature or different signs of temperature? I will ask Kushi Dangi, do you have any doubts?
No, sir.
Okay. Nikita, you have any doubts for this seesaw event? Do you understand the concept?
No, sir, I understand.
You understood, right? Okay. Okay, fine. I also suppose Arjun has understood the concept.
Yes. Yeah.
Okay. That's how this younger dress or the
Boi- Boiling.
bowling Alerod events, these were uh, occurred during the last glacial period. Okay, the next question in this context is why was the Laurentide ice sheet influential in slowing down the AMOC? Okay, so I will ask that questions from here. Okay, so I will try to explain that. There were massive amount of ice sheet in this region, and this ice sheet somehow went towards the eastern part and they deposited into the northern ocean. Due to that, there were changes in the Atlantic Meridional Ocean circulation. Now, I am just repeating that there were massive ice sheets here, and these sheets travel towards the east in the Greenland Ocean, or I don't know the name of the sea, let's say North Atlantic Ocean, and these were deposited in that region, and that changed the Atlantic Meridional Ocean circulation. Now, I would ask you why that changed the circulation in the first place. What was the main driver which changed the strength of the circulation and why it should change? So, okay, so I would like to ask you to, okay, Khushi, can you just give some explanation for why that ice sheet should change the circulation, ocean circulation? I'm just opening the mat again. Any idea, any concept, or anything you can say about it. How it can affect the circulation? Yes. Okay.
When ice sheets actually melt
Hmm.
and go into the ocean, the salinity would decrease.
Yes. Right. That is one factor. And what is the second factor? That is for salinity. And the second factor is for what is the temperature difference between ice and water? Yeah, both are preferably at 0 degrees Celsius, but there
Yeah.
is a difference in the latent heat. So that's, I think,
Oh,
somehow.
okay, okay. It is released. Okay.
So if some water is, let's say, above 0 degrees Celsius, that will bring the temperature down. That's how it should work. So basically, it will disrupt the cycle. It will weaken the cycle because if there is fresh release of uh, fresh water or release of fresh water in this region, that fresh water will lie towards the top of. I mean, there will be inclusion of fresh water, and that will stop. That will actually decrease the salinity of the ocean, Atlantic Ocean water that is already coming. If the salinity is decreased, then the density will also decrease because saline water is more dense. So the downwelling of that water, where it went down, that process will be quite weak, and that might even stop the Atlantic Meridional Ocean circulation that we are afraid of. That might happen in the near future due to the carbon dioxide release or increase in the temperature and not release of a lot of fresh water in this region. But it will decrease the strength of the Atlantic Meridional Ocean circulation because it is tied within a single pattern. So if one part is disrupted, one part is stopped, then the whole circulation will be affected. And it will be less efficient in transporting heat from this equatorial region to the polar region. If it transports less heat, then it will incur uh, decrease in the temperature or colder temperatures here. It will cause that warmer temperatures here. That's how it caused this time era. So weakening the downwelling of the AMOC, therefore weakening the AMs. That was the role of the Laurentide ice sheet, and it was actually uh, very interesting event because if there is more snowfall, then there would be increase in the ice sheet, and if there is increase in the amount of ice sheet, then the sheets will eventually go towards the North Atlantic Ocean, and they will decrease the circulation of the AMOC, and more snowfall actually requires temperatures below zero, but not too low. If the temperature is too low, then the snowfall will not occur. We might have a misconception that if the temperature is very low, then there will be heavy snowfall. But it is not always true. There is an optimum range of temperature in which the snowfall is the highest. If the temperature is below that, then the snowfall will also be lower. So there was some, let's say, warmer event. Let's say it is below zero, of course, but not too much below zero. So there will be high snowfall in that at that point, and that will in the Greenland region that will decrease the temperature via the weakening of AMOC. So that is the concept of increase and decrease in the temperature during that period. Boiling alley rod or younger dryas, older dryas, oldest dryas, this type of events. Any doubts about this?
That's okay. That's okay.
Okay, Nikita, any doubts? Or shall I explain? You understood, or shall I explain again? Or okay, Nikita is also not there. Okay. So there was a question on the flow rate in the assignment, I suppose. So we can solve a similar question, and we will get an idea of how to solve this type of questions. The question is, the Kuroshio current flows at a volumetric rate of 30 sweat drops. Sweat drop is nothing but 10 to the power 6 meter cube per second near some point, Taiwan coast. And assume that the flow is steady. So the flow rate is constant. Flow is steady means the flow rate is constant. Estimate the time to complete a spherical ball which has the radius of moon. So that is a very simple question. But what would your approach be? How would you solve that? Forget about the calculations, but just tell how the concept or how the method for solution of the question will be. You hide that. So you have to fill a spherical ball that has the radius of some value, and you have to feel that you are given a flow rate. Okay, so can you assist in solving that? The basic approach. What will you do?
The volume of the spherical ball will be 4 by 3 pi r cube. That
Okay,
is
fine.
flow rate is
Yeah,
amount
some unit. You don't need
volume
to.
in a second. The amount of the volume in a second, right?
Right,
Is
right.
it?
So if you, yeah, you have volume per
So
second, you have volume here. So in order to
div-
determine the time, you have to divide it by,
divide. Okay.
and last is the calculation. I have done that. Might be right, might be wrong, but I have done something. But the main approach is like that. By the
Okay.
way, in this calculation, that will take 23,205 years to complete
So
spherical ball. I think in your assignment you have similar questions. That's why I put that.
okay. Thank you.
Just I cannot put the exact question, but similar question. Oh. The second question is about, of course, it is on the flow rate. Now, the water quantity of Earth is 1.386 times 10 to the power 9 kilometer cube, and we build a cylindrical reservoir with base, some circular base. What would the height of the reservoir be? So it is a, I mean, I think this is a pre-university college type uh, question for geometry or something.
Okay, so the volume is pi r square h. So pi
Right.
into base radius whole
Yes,
square into
yes.
height.
Yeah, that is a question of measurements. So that is the simple question. Actually, I was uh, looking at some results. I mean, it is a very simple question, but I was looking at this fact. Uh, let's say I will search like water of Earth into a sphere. If I will be lucky if I just get the picture of that. Okay, yeah, I got the picture. So see that picture. So this is Earth's water, which is concentrated into a sphere, and the sphere is, I mean, very small. The radius of the sphere is very small. I think, let's say, the diameter is 2000 kilometers or something like that. So we only have this much of water on Earth. At first instance, it looks surprising, but later we should consider the fact that the Earth has a much deeper core, or this
Water
crust.
depth.
Yeah, and this is concentrated into a sphere, and the sea is only 4 kilometers deep on an average. That's why if you concentrate all the waters into a sphere, that will be a very small, tiny blob. That will, I think, it is equal to one of the states in the United States, or maybe one of the states in India, or let's say half of India, something like that. That
Okay,
is
okay.
the amazing fact. I mean, not amazing, it is a very evident fact, but at first instance, it looks little surprising that we have very tiny amount of water. There are planets which are completely covered in water also.
Exoplanets.
There are different exoplanets. Maybe water or liquid methane, different chemicals are there. So much of wonder. Anyways. Yeah, in your question, I think you are given an exoplanet which is completely water. So the next question is on heat transport. Uh, yeah, before asking the question, I should go to the basic formula for the heat transport. Uh, the heat transport Q is the mass times the specific heat capacity times the temperature difference. Because if there is more temperature difference, there will be proportionally more heat transferred from one body to another. If there is more mass, the body is massive, then it will of course release or absorb more heat, linearly proportional. And a constant is basically defined depending on these two factors, which is known as specific heat capacity. The constant is interpreted that if there is a high value of the specific heat capacity, it will be able to store or release more heat given a fixed temperature difference and a fixed mass. That's how the equation goes. Q equals to m times Cp times delta T. Now for flows or for liquid or fluids, you can express the m in terms of rho or the density times the
volume.
volume. M equals to rho v. That is the basic concept. And if it is flowing, then you can also define heat rates, which is the rho times dV/dt. Basically, the uh,
Sorry,
volume change of volume per unit time because it is flowing.
sorry.
So, and in that case, it will also be dQ/dt, not Q. So that is the basic
Okay.
concept for solving this type of questions. If water is flowing and it has some temperature difference, then it should transport some amount of heat depending on its mass as well as the specific heat capacity. And mass is dependent on the volume or the flow of the volume that is occurring because fluids flow from one place to another. Okay, so we assume some steady flow with temperature difference, steady temperature difference, and we will see how much heat energy is transported from one place to another. In this question, we have volumetric flow of 20 sweat drops from south to north across the coast of Philippines. The characteristic temperature difference is 7 degrees Celsius because you know that the temperature difference is mostly maintained. So the tropics are usually warm, the polar regions are usually cold. So there must be heat transport in order to maintain those type of temperature differences, whatever it is in steady state. The density is given as 1006 kg per meter cube and the specific heat capacity is 3993 joule per kg per Kelvin. Now, for calculating the power transported, power is basically energy per unit time, which is Q by T. Heat is also one form of energy. That's why we just plug in the values of Cp, M, and delta T. For M, we have replaced rho times V, and we have the V by T, that is 20 sweat drops, 10 to the power 6, 1 sweat drop is 10 to the power 6
Okay.
meter cube per second. We have just put in the value, and here is the value for the density, here is the value for the specific heat capacity, and together, of course, there is the value for the temperature difference. Together, we get the power transported. And just for some excitement, we put the world's power capacity of 9,000 gigawatt, which can be comparable to that flow, which is 63.67 times the world's power capacity. Giga means 10 to the power 9, so it is 9 times 10 to the power 12. It is 5.73 times 10 to the power 40. So just we can divide this by this 9,000 gigawatt and we will get the fraction of 63.67. I think in your question,
Okay.
assignment question also there is some power related stuff which asks about the India's power consumption and asks you to derive the number of such countries that will fulfill the power. I mean, that will be equal to the power. Let me ask Nikita. Nikita, you uh, understood this problem or shall I repeat?
सर रिपीट कर दीजिए वो क्लास कट गई थी
Okay, so shall I repeat in Hindi or
हिंदी सर
okay, Arjun? So I will just try to explain the same thing in Hindi. Is it fine?
That's fine. It's fine.
Okay, I mean, I explained to you, but she was not there. So okay, so I mean, Hindi is not my first language, so I take pardon for that, but I will try. So the Q is the heat transported, कितना ताप संचारित हो रहा है, ओके, वो निर्भर करता है mass मतलब mass, I mean I don't know the Hindi for mass. CP is the specific heat capacity, मतलब कितना बेसिकली एक अनुमान है कितना ताप वो धारण कर सकता है, और T है टेम्परेचर डिफरेंस, तापमान का जो अंतर होता है उसके साथ संपर्कित है, और इसके इसके द्वारा हमें ये समीकरण मिलता है कि Q इक्वल्स टू M टाइम्स CP टाइम्स डेल्टा T कि अगर अगर आपको ये सभी का मान पता चल जाए, सभी का वैल्यू पता चल जाए, तो आप ये बिठा के कितना ताप संचारित हो रहा है किसी भी वस्तु के द्वारा आप ये निकाल सकते हैं। अब फ्लूइड के कंटेक्स्ट में, फ्लूइड के क्षेत्र में हम मास को डेंसिटी टाइम्स वॉल्यूम द्वारा प्रकाशित कर सकते हैं, ओके, बिकॉज मास इज डेंसिटी टाइम्स वॉल्यूम। तो ये क्यों करेंगे, क्योंकि हमारा जो वॉल्यूमेट्रिक फ्लो है, कितना आयतन है उसका, फ्लो का, वो कितना तेजी से संचारित हो रहा है एक जगह से दूसरी जगह में, उसका मान है 20 स्वेट ड्रॉप। इस सवाल में आपको स्वेट ड्रॉप के बारे में पता है या नहीं है? अगर नहीं है तो मैं एक बार बोल देता हूँ, स्वेट ड्रॉप, वन स्वेट ड्रॉप इज 10⁶ मीटर क्यूब पर सेकेंड, ओके, कितना वॉल्यूम, कितना आयतन वो जा रहा है उसका एक प्रति सेकेंड में, उसका एक परिमाण है। अब डेंसिटी दिया हुआ है 1026 केजी पर मीटर क्यूब, हीट कैपेसिटी भी दिया हुआ है 3993। आपको बस गणना करना है कि कितना पावर इसके द्वारा संचारित हो पाएंगे, और ये जो पूरा विश्व का जरूरत है पावर का, क्षमता का, वो 9000 गीगावाट, उससे तुलना करना होगा। कितना करीब है, कितना गुने अगर करे उसके मान मिल जाएंगे, ठीक है। तो हम पावर इक्वल्स टू क्यू बाई टी, सीपी टाइम्स ये एम बाई टी कर दिया, क्योंकि बाकी सब कॉन्स्टेंट्स है, और एम के जगह हम रो कांस्टेंट से वी, आपका जो वॉल्यूमेट्रिक वो वी बाई टी मिल रहा है, तो उसके जगह हम 20 स्वेट ड्रॉप जो है उस वैल्यू से प्रतिस्थापित करेंगे, और जो डेल्टा टी दिया है तापमान का अंतर, वो है आपका 7 डिग्री सेल्सियस, वो 7 यहाँ बिठा देंगे, ठीक है, तो 7 बिठा दिया, 20 स्वेट ड्रॉप 20 × 6 बिठा दिया, 1026 जो है घनता, जो एक 1026 ये बिठा दिया, और स्पेसिफिक हीट कैपेसिटी जो है 3993 जूल पर के जी पर टूल, वो भी बिठा दिया। एक साथ गणना करके हमें ये सब मिला 5.73 टाइम्स 10⁻14 वाट्स, और इसके द्वारा अगर हम भाजित करेंगे तो मिल जाएगा कि कितना गुणे है इसका। तो 1 गीगावाट मतलब 10⁻9 वाट्स, तो ये है 9 × 10⁻12 वाट्स बेसिकली, और ये मिला 5.73 उसके द्वारा हम किए हैं 10⁻14। सो ये अगर आप इससे ये भाजित कर देंगे तो आपको मिल जाएगा 63.64 के आसपास, 64 टाइम्स द वर्ल्ड्स पावर कैपेसिटी, ओके। आपके इस एक ही तरीके का सवाल आपका असाइनमेंट में शायद दिया हुआ है, इसलिए मैं इसको यहाँ व्यक्त किया, ओके।
ओके सर।
We convert Celsius to Kelvin.
1 डिग्री सेल्सियस इज बेसिकली इक्वल टू 1 केल्विन, राइट? Celsius. Oh, okay, okay. You are asking the formula.
Yeah, should we convert Celsius to Kelvin?
See, I mean, Celsius to Kelvin, the what is the formula for Kelvin?
Plus
Kel
2/3.
Kelvin is Celsius minus 273.15, right?
So should
So,
we convert 7 degree Celsius to
so for
273
the
plus?
context of the question, you can convert, but you know, as the difference in Celsius is equal to the difference in Kelvin,
Oh,
because
okay.
273.15 is a constant. Then the delta
Uh,
T will not make one change. If I increase something by
mm,
1 degree Celsius, it will also increase by 1 Kelvin. So the
yeah, that's
differences will always be the same. Yeah, but of course, if you are given some questions in which you have to find the temperature in Kelvin or Celsius, then you have to always respect the units.
okay. Thank
The
you. Thank
problem arises when it is given in Fahrenheit, because one Fahrenheit difference is 5/9 say degree Celsius different. 1 degree Fahrenheit is equal to, 1 degree Fahrenheit difference is equal to 5 by 9 degree Celsius difference, or 5 by 9 Kelvin difference. In that case, you should be careful.
Thank you.
Okay, so the next, okay, I have another question on heat transport. Okay, uh, with an increase in the amount of absorbed heating, the temperatures of both land and ocean will increase. That's fine. Assume that the Indian Ocean has surface area of this one, 7 into 10 to the power 7 kilometers square. Calculate how much heat is required to warm the top 500 meters of the Indian Ocean by 1 degree Celsius, which is basically 1 Kelvin. Assume rho and Cp is given. So, okay, okay, I will now ask you for the approach. Nikita, can you just help us in solving the question? Just a basic concept. You can tell in Hindi, no problem. This question, what would your approach be for solving that question? Question
सर
asked.
ये जो भारतीय महासागर
हाँ हाँ, yeah, please.
भारतीय महासागर का क्षेत्रफल
Hmm.
7 multiplied 10
Right.
वर्ग किलोमीटर.
Right. Yes. Then
आई ट्राई मैं ट्राई कर सकती हूँ वैसे. तो मतलब उसको ऊपरी जो सीमा है उसको 5 मीटर जल 1 डिग्री सेल्सियस गर्म करने के लिए उष्मा चाहिए होती है.
yes.
And
Okay. So you need to find आपके ताप कितना जरूरत है वो निकालना पड़ेगा. You need to find the heat which is required to warm. So uh, you have to find the volume first, right? क्षेत्रफल.
yes,
You have got the surface area or क्षेत्रफल, and you have got the गहराई or the depth 500 meters, right? So if
sir.
you just multiply these two, you will get the volume ayatan, right?
Yes, sir.
Then if you have got the volume, then how would you find the mass? You have given the घनता, the density. What is the formula for
घनत्व
mass? Yes.
वो क्षेत्रफल मल्टीप्लाई गहराई.
Yes, yes. Okay, so rho times the area times the height, right? Or the depth, right? Good.
यस सर.
So the rho times the volume. Okay, fine. So you have got the mass. You have got the mass, you have got Cp. You have also got the temperature difference. तापमान का जो अंतर है. Then how would you calculate the heat required? What is the formula? Actually, it is written. So Q is mass times Cp times delta T, and you have got all the values here. So you just need to put the values, and it will give you. The calculation. I'm just keeping the calculation. It will give you 3.5875 into 10 to the power 98 kg for the mass, and Q is m times Cp times delta T. You put the mass here. You put the Cp value of Cp here, and the value of delta T, which is 1 degree Celsius or 1 Kelvin. You will get the final value of 1.435 into 10 to the power 23 joules. So that is the first part. Okay, and the second part, in the second part, I will ask the question that it is absorbing power at the rate of half of the solar constant. Let's say there is solar radiation daily solar radiation in that region. We will not assume exactly 1360, but we will assume half of that. So I think 68 or something. Yeah, 680 watt per meter square, something like that. So estimate the time for Indian Ocean to warm up by 1 degree Celsius. How do you solve this? So you have got the heat required to uh, warm the ocean by 1 degree Celsius, you have got the power. Okay. Now, how do you solve this? That is the second question.
Power is heat by time.
Right,
So power by heat capacity, heat will no, okay, heat by power will give the time required.
right. So power is heat by time. So time is heat by power. Exactly, we have done that. So here, the heat required is rho times A times H times Cp delta T, and the solar irradiance is assuming S by 2,
Right.
and then area will be actually cancelled, so there will be no role of the area. It will completely be area independent of area. So here we have just put the values: the density 1025, the value of height 500 meters, specific heat capacity of 4000 joules per kg per Kelvin, and the delta T value of 1. And here we have just inserted the value of S by 2, and it will give us 3.015 into 10 to the power 6 seconds, which is close to 35 days. Now the question is, it happens, right? Daily the solar radiation is there. Of course, there are clouds or something, some things are there. But using this rate, let's say it is not 30 days, let's say in 1 year, it is, if it continues daily, then the temperatures of the ocean would increase, right? All of the oceans would increase, but it doesn't increase. What is the main reason for that?
Could you repeat the question, please?
So solar radiation is there, right?
Okay.
And using this calculation, if it is absorbed properly, then it would increase the temperature by 1 degree Celsius in 35 days, right? Using
Yes.
this calculation. Okay, let's say we have done some overestimation in the calculation. So let's say it takes 3 months or 4 months to increase the temperature by 1 degree Celsius, but it would increase. But in reality, the temperatures of the oceans remain mostly constant. What is the reason that it is in a steady state or the temperatures don't increase, though it absorbs a lot of heat? That is the question. Just qualitative answer. Quantification is required. Yeah, I'm just
Actually,
asking.
time is more. So, uh,
Yeah, you will get some time. That is fine. Using this calculation. But there is something we have which we have assumed wrong, which we have not taken into account. The simple is the system is not that simple. So there are different processes. Let's say outgoing long wave radiation, distribution of heats due to convection, advection, this type of processes. Many more processes are involved, which we have completely ignored. We have just looked into that particular solar irradiance, which is not true. So all the processes actually try to distribute the heat and also try to release the heat in terms of outgoing long wave radiation. That's why these things are mostly in a steady state. Okay, that's why uh, the temperatures really don't increase. Okay, okay. So Nikita, shall I repeat the question for you, or is it fine? The second part.
हाँ सर, आप आगे करवा दीजिए, वो नेटवर्क इश्यू था थोड़ा-सा।
Shall I go forward or shall I repeat?
फॉरवर्ड कर दो।
Okay. Okay. Uh, Now we will talk about salinity of ocean. Uh, so the unit of salinity is the practical salinity unit or per mil. Per mil means parts per thousand, or how much of mass of salt is present in 1,000 grams of water. That is the definition of the salinity. So yeah, how many grams are present in 1,000 grams of water? How many grams of salt? That is the definition of salinity. And oceans have an average salinity of 35 ppt. And uh, yes, the salinity in the ocean depends on difference between evaporation and precipitation. So yeah, I will uh, ask you why it depends on evaporation and precipitation, or can you do you know the salinity structure of the oceans in the world? How are they? How they look like? Where did you expect more saline water? Where did you expect less saline water? Qualitatively, Nikita, you can answer that.
सर ये लवणता का अर्थ आई मीन 1000
Right,
1 किलोग्राम समुद्री जल में जो घुले होते हैं ना लवण
right.
उनकी
Khar,
नमक की मात्रा को मापते हैं ना
khar,
पीपी
khar, yeah,
पार्ट्स पर
kharapan, right?
यस सर
Yeah, that is the PPT. But I am asking you, सवाल है कि जो सैलिनिटी का अंतर है विविध सागर महासागर में, उसका कारण आप कैसे वर्णन करेंगे? What is the reason for differences in the salinity across different oceans or different seas in the world? Now
मतलब
I'm
खारे और मीठे पानी की तुलना में सर वो बताना है क्या?
यस यस कहाँ खारापन ज्यादा होगा कहाँ कम होगी वो आपको बताना है इन टर्म्स ऑफ इवेपोरेशन एंड प्रेसिपिटेशन कितना अ, वाष्प बन रहा है और कितना बारिश हो रहा है उसके उसके द्वारा
सर अधिक वर्षा मतलब जल की मात्रा बढ़ जाती है तो इससे तो लवणता कम हो जाएगी मतलब सैलिनिटी कम हो जाएगी अगर वर्षा
राइट
ज्यादा हो
एग्जैक्टली एग्जैक्टली एंड
और इवेपोरेशन मतलब अगर ज्यादा मतलब जल की मात्रा कम होगी तो नमक में सांद्रता बढ़ेगी अगर जल कम होगा तो उससे लवणता तो ज्यादा ही होगा उसमें
ओके नाउ टेल मी वेयर more evaporation occurs less precipitation occurs when less evaporation occurs more precipitation occurs कहाँ वर्षा ज्यादा होता है वाष्प कम बनता है कहाँ उल्टा होता है
वर्षा सर जहाँ वास्तविक वाष्पीकरण मतलब सर अधिक होती है वहां पर तो वर्षा कम होती है और वहां पर ह्यूमिडिटी ज्यादा होगी सर
So at what regions धरती के किस किस हिस्से में आप यहाँ की इसका आशा कर सकते हैं मिड लैटिट्यूड ट्रॉपिकल रीजियन पोलर रीजियन सब ट्रॉपिक्स
सर वर्षा तो ज्यादा तो उस पे ही होती है इक्वेटर पे वर्षा तो वहां पे होती है
राइट राइट बट इवेपोरेशन इज ऑल्सो हाई देयर राइट
यस सर
एंड इन द सब ट्रॉपिक्स द रेनफॉल इज लो बिकॉज यू कैन सी मोस्ट ऑफ द डेजर्ट्स आर इन द सब ट्रॉपिकल रीजियन राइट रेगिस्तान जो है वो सब ट्रॉपिकल रीजियन में ही स्थित है ज्यादा से ज्यादा
यस सर
so the evaporation is higher but the precipitation is not that high so the
ओके सर
regions at which वहाँ जो सागर होंगे the oceans or the seas will have higher values of salinity okay
यस सर
so we can expect that in the subtropics the salinity will be higher in the polar region polar uh, I don't know what you call for polar in Hindi
ध्रुव ध्रुव सर
okay so there you will have a lot of glaciers right so
ओके सर
बर्फबारी हिम Himkund, जो, so that will be there, and that will include fresh water in those regions. So due to that, the salinity will decrease or increase. मीठा पानी अगर आता है ज्यादा salinity increase होगा या decrease होगा?
कम होगी सर
So that is in the polar regions the salinity should be lower. In the tropical region it will be let's say moderate, might be higher, but in the subtropics it should be the highest. Another thing is there, uh, confinement of ocean. Now I will ask this factor to Arjun. So if an ocean or a sea is mostly confined, there is not much flow into the sea or ocean. Would the salinity be higher or lower?
Remain the same, right? Okay, could you repeat the question, please?
Let's say you have a sea or ocean which doesn't have much connection with outside oceans. Then the salinity would increase or decrease in that region. Of course, it depends on the evaporation and the precipitation. But assume that the evaporation is more compared to the precipitation. I am specifically talking about the Mediterranean Sea. In the Mediterranean Sea
If
region,
evaporation more
yes,
than salinity would increase. If evaporation is greater than
right,
if
yes, the Mediterranean Sea. I think it is Bhumodhya Sagar or something in Hindi. So in that region, the evaporation is more compared to the precipitation, but it is also not connected to outside ocean. I mean, there is a connection at the Gibraltar Strait with the Atlantic Ocean, but the connection is not very strong. So the salinity there is quite high. And there are different lakes which are situated in the subtropical regions. You know about the Dead Sea?
No, I have heard of it, but I'm not.
Okay,
I
so the Dead Sea is a sea in which if you try to swim, you will never drown, even if you don't know swimming. Okay, so
okay.
so Nikita, have you heard about Dead Sea?
Yes, sir.
Have you heard about Dead Sea?
That Simrit Sagar.
Right, right. So here, if you try to swim, आप अगर तैरने की कोशिश करिए, तैरना नहीं भी आता, फिर भी आप डूबेंगे नहीं. That is the reason. The reason is the salinity is very high. If the salinity is very high, then the density is also very high. And now I just want to tell why the salinity is very high, because rainfall is very little in that region, but the temperature is high. So the evaporation happens. And due to that long process throughout many years, the salinity kept on increasing and now it is very high.
Actually, I'm just asking, doesn't precipitation actually vary according to season? I mean, in monsoon it'll be highest, right? So seasonal variations will won't it come?
Oh, okay, okay. Seasonal variation of salinity. Yes, yes, of course. It is a very important factor in different oceans, and people often study about it. Let's say in the Arabian Sea, if the monsoon occurs, then the salinity will be lower. And in Bay of Bengal also, we know there are different rivers which uh, merges into the Bay of Bengal. So after the monsoon season, there is inclusion of a lot of fresh water, so the salinity basically decreases. And for this season, let's say it is now the month of February, the salinity will be higher in the February,
So
March.
AMOC won't it also depend upon will it depend upon season?
Atlantic Meridian Ocean circulation, will it? I think yes. I think it depends on season, because the trade winds are a major factor for controlling the AMOC, and due to the trade winds, they actually shift towards the north or south depending on the season. Towards the uh, northern hemisphere summer, they shift towards the north, and the northern hemisphere winter they shift towards the south. But actually, the main driver, there are two parts. One is the surface water. The surface water will be controlled by the seasons, but the deep ocean water, I think that has a strong impact, or that has very strong, robust type of structure or circulation. That's why it will vary. But whenever we talk about AMOC, we talk about
Global.
the average picture that happens throughout and that is a mean value of the year or something like that. So it will vary according to season, because the Gulf Stream is also weakened or strengthened depending on the seasons, and the westerlies they also change positions, of course. But when we talk about the AMOC, we talk about the mean value or the value in a year. Do you have a graph for AMOC? I don't know. Let me check. Just let me check graph of AMOC. I find that. Ah, right, right, yes. Yeah, you can see smaller peaks, right? Here in the graph. The
Yeah.
smaller peaks might correspond to the seasonality. Okay. So it is not a very smooth thing, or it is not always, it is never a constant. It always varies with time. So, but we take the mean value. That's why we average over some time period or 1 year, and then we see for the mean value, because it changes with time. But after a year, it repeats back to the original position or the original values. If I
Okay.
just AMOC year, actually didn't talk about it much, but I can see smaller peaks here. So yeah, there is always some seasonal cycle associated with that. In fact, if you take any variable in the atmosphere or ocean, you will always find smaller peaks which correspond to the seasonality. So the seasonality of many variables are there, but it also depends on the strength of the season. For example, in Indian region, the seasonal variation is very high. Monsoon, the wind blows from southwest to northern direction, and in winter it blows from east or northeast to south or southwestern direction. The seasonality is very strong, and it also changes the direction of the flow into the Bay of Bengal, Arabian Sea, these regions. And at other regions of the world, the seasonality is not very strong. I can show you one graph which is about ITCZ variation. Let me see if I get some image of the ITCZ variation. Okay, just see the graph. Okay, so this is the intertropical convergence zone. So in that region, you will expect very high rainfall uh, in the different times of the year. Okay, I think I'm just going to just make sure. Nikita, you are on with us, right? So I'm talking about the seasonal variation.
Yes, sir.
Okay, so he asked the question. ये सवाल पूछे है कि ये जो मौसम के साथ साथ ये चीजों का एएमओसी बोलिए जो भी विंड पैटर्न बोलिए इसका बदलाव होता है या नहीं होता है और यह कितना प्रभावित करता है सर्कुलेशंस को। ओके, ये इसका सवाल है, अर्जुन जी का सवाल है। Now, I am trying to show one such aspect. It is the ITCZ. ITCZ means the, let's say, assume it is the region of very high rainfall or wind convergence zone. Here the north and the south winds they meet. Okay, south north trade winds and south trade winds they meet. So you can see at this region the variation is not much. यहाँ ज़्यादा बदलाव नहीं हो रहा है. But in Indian region that is there is a huge difference. In Pacific region there is a huge difference between the north and the south for the time of July and January. So in these regions the seasonality will be very strong. But in the Atlantic regions the seasonality will not be that strong. So it depends on
Could
the
you
region.
please explain north and south trade winds? Not familiar. What is
Okay, okay. Trade winds are basically the winds that prevail from the subtropical region to equatorial region. Because the temperature in the equatorial region as well as the pressure temperature is high, pressure is low. And in the subtropical region, pressure is high, temperature is low. So in order to balance, there is a wind flow from north to equator and also south to equator. That is called the trade winds. Okay.
okay?
And the position of the trade winds, they are sometimes used to define the position of the ITCZ. ITCZ means Intertropical Convergence Zone. Both north and south trade winds meet at some position in the world that also changes with respect to seasons. This is known as Intertropical Convergence Zone. So there is almost no flow of winds, but high rainfall associated to that. So that's how we define ITCZ. One definition. There are multiple definitions of ITCZ. Just to show that the wind patterns actually change, there is seasonality in wind patterns, seasonality in rainfalls. So there will be also seasonality in North Atlantic Indian Ocean circulation. Okay.
Okay. Okay.
Huh.
Thank you.
Right. Okay. Uh, where was it? Okay. Salty water is denser than fresh water, and the density difference will play important role in thermohaline circulation. Very obvious. Sea surface salinity shows regional and seasonal variation due to environmental conditions. Salinity also varies with depth. Now there is a catch in lower latitudes because there is more evaporation towards the surface of the ocean or the sea. The salinity will be higher because there is more evaporation, so less amount dissolving. It dissolves more amount of salt at that shallower depths. And at greater depths, the salinity would decrease. In higher latitudes, the surface water is actually cold and it doesn't incur much evaporation. So the salinity will increase with depth because the deep water is more saline and the density is higher. Okay. सो खारापन ज्यादा होता है गहराई में, तो इसके लिए सैलिनिटी बढ़ता है डेप्थ के साथ, घनता ज्यादा होती है. In lower latitudes, the surface salinity is higher because evaporation वाष्पीभवन ज्यादा होता है. इसके लिए salinity भी जो surface water है ऊपर के सागर के ऊपर के हिस्से में जो पानी है वहाँ salinity ज्यादा होता है. उसके बाद जो गहरी होती है गहरी पानी में salinity घट जाती है. There is a picture for salinity of oceans as we have discussed. The regions in the subtropics, you can see there is less saline, there is more saline water in the subtropical region because there is more evaporation and less precipitation. And in the polar regions, the water is very low in salinity. You can see in North Pole or South Pole, the salinity is low because there is fresh water from the uh, icebergs, ice sheets, and also very less amount of evaporation that happens in this region. I think below zero there is should not be any evaporation. And the salinity is mostly high in the subtropical region. The Mediterranean Sea has very high level of salinity. Even in the Arabian Sea, you can see high salinity, and that is an important difference between the salinity between Bay of Bengal and Arabian Sea. Bay of Bengal is fresh, less saline compared to the Arabian Sea. Okay, that is the basic structure. Now the question on salinity. The question is similar to the question that is given in the assignment. So we want to make electrolyte solution uh, in amount of 250 milliliters with a salinity of 9 PSU. So how much salt would we add to each of the packets? Okay. Now the definition of 1 PSU is if 1 gram of water is dissolved into 1000 grams of water or 1 kg of water, then salinity is 1 PSU. So the definition of 9 PSU is 9 gram per kg, 9 gram per 1000 grams or 9 gram per liter because the density of water is almost 1. I mean, 1 is 1 gram per cubic centimeter or 1000 kg per cubic meters. Okay. So for getting the amount of salt in 250 milliliter, we just need to multiply it by 250 and divide by 1000. So we'll get 2.25 grams of salt in each of those packets. That is the value for salt. Okay. Any doubts on this first question?
It's
Yeah,
fine.
it's fine. Straightforward question. Nikita, any doubts?
No, sir.
Okay. And the second question is, we discovered a new planet. Okay, this is the exoplanet, which has radius of 7,000 kilometers, and it has 50% ocean of water with, I mean, by surface area. And the depth is 5 kilometers. The ocean has some amount of salt, 9 into 10 to the power 21 kg. We have to calculate the salinity. So what would be your approach be for that? Can you tell me? You are given the amount of salt in the ocean. You are given different parameters, let's say surface area, depth. How do you calculate the salinity?
Amount of salt divided by volume, right?
Okay,
Volume.
then you will just compare it to the definition of the standard salinity unit or practical salinity unit, right?
Yeah.
Okay. Uh, any doubts, Nikita? It is a very straightforward question.
No, sir, no doubt.
No doubts, right? Yeah, basically you need to find the volume of the ocean water. For yeah,
Papayas.
I will just ask you. So what is the formula for the volume of a sphere? Not
Papayas.
not Arjun, but Nikita.
Yes, sir.
What is the formula for volume of a sphere if the radius is r?
Sir, uh, volume is equal to 4 pi r,
4
uh,
pi r?
r, pi r, r स्क्वायर मल्टीप्लाई जो डेप्थ है और मल्टीप्लाई 0.5 शायद सर यही होगा।
Yeah, I mean, yeah, I asked for a volume of a sphere. If the radius is r, then it is 4/3 pi r cube. But you have given formula for the volume of a more difficult thing, which is a spherical shell, which has depth of h and radius r. And if that is there, I mean, of course, that is in the question. The question we have just asked that. So 4 pi r squares times the depth, which is the volume of the spherical shell, which we have assumed to be uh, the shape
So
of the ocean. That is fine. So
for a
we'll
shell, isn't it 4/3 pi into outer radius cube minus inner radius cube?
yes,
Isn't it
yes,
all?
yes, yes, that is true. But for this type of thin shell, we can approximate. Yeah, for exactly if it is having two spheres, then the volume will be 4/3 pi r cube, the outer sphere minus 4/3 pi small r cube, the inner sphere. But if it is a thin spherical shell, at least in that question it is thin spherical shell, then you will get the volume as 4 pi r square times the depth. Okay. Or basically this is an approximation. Okay, so we will get the salinity from this calculation as well. Okay, then the next uh, section we will ask questions about AMOC. If AMOC becomes stronger, uh, how and why the flow rate of North Atlantic water will change? We have discussed that. So it will also increase because there is a continuous circulation, and if one part of the circulation is strengthened, then the other part will also become stronger. So AMOC and NADW both will have an increase. Now, there is an informative question. Wind actually mixes the shallow layer of the ocean with the surface up to a few hundreds of meters in the oceans. Let's say salinity temperature, they are well mixed. But how much mixing happens at the deep ocean? The answer is there is almost no mixing in the deep ocean. Uh, so if there is no mixing, then examining the water would tell us where the temperature, what the temperature and salinity is, and where that water came from. It came from Greenland region or Antarctic region or any other region, we can easily tell. So that is the property of the deep ocean water. That's how we are able to estimate the thermohaline circulation related climate evidences from that. Okay, now there were two events in which we saw the warming. One was between 15 to 13 kilo year ago, and another was between 133 and 131 kilo. Uh, Actually, km is actually 1,000 years. Actually, yes. So uh, there were differences between two events. In first case, the 15 to 13 kilo year ago event, uh, the temperature in the southern hemisphere was below normal, while the temperature in the northern hemisphere was above normal. While in the 133 to 131 kilo year ago, that event, the temperature was above normal in both the regions, southern and northern hemisphere. And the current greenhouse effect or the global warming is analogous to the 133 to 131 kiloyear event ago. That's why it is more important. Because the whole Earth is warming. Okay, now the next question is about the subsurface temperature for these two events. So warmer temperature, surface temperature prevailed during the 130 to 131 kilo event compared to the 15 to 13 kilo event. Okay, here is the vertical structure of AMOC. Now here is the northern region, here is the southern region. This Gulf Stream or the stream that prevails toward the North Atlantic releases heat and it sinks here and forms the North Atlantic deep water for maintaining the circulation or maintaining the continuity equation, it comes back to the southern region, and there it experiences upwelling, and it then uh, gains some heat, and again it completes the circulation, and it also enters the Indian Ocean or Pacific Ocean, this type of region. There is another uh, deep water circulation which is known as Atlantic bottom water, which is the densest water, and this is very deep. Okay. Okay, now just for uh, the concept of glacial and interglacial periods, we have experienced several glacial and interglacial events throughout the history. Some recent events are given here. The glacial events are generally longer, which last between 70,000 to 90,000 years, and interglacial events are shorter, 10,000 years. Now, currently, we're in the interglacial event, and that started actually 10,000, 11,000 years ago. That is also known as Holocene eh, time, Holocene period. But unfortunately, due to climate change or the increase in the temperature, we are not getting the uh, glacial period intention, that is the difference. So, considering the natural variability, the glacial times should come within a few hundred years, but it is actually being pushed and it is delayed. In fact, we are experiencing increase of temperature in that in the current days, starting from pre-industrial revolution. And in the last glacial events, there were two events: Bowling Elrod and Dryas. The Bowling Elrod was a warming event, and Dryas that was cooling event, which is also known as stadials. And this warming event is known as interstadial. Okay. Okay, so after that, the temperature reached a stabilized value, stable value, which is known as Holocene, and we developed agriculture civilization after this time, the last 10 years. And yeah, there are also, just to mention what events were there. So, Dansgaard, Oshkar events, these were rapid fluctuations in temperature in the last 80 or 80,000 or 1 lakh years back. So we can see rapid warming and slower cooling at different points of time. And these events actually are evident in the paleontological evidences from the data across sea basins or coral reefs or let's say continental sediments. It's this type of evidences we have got from these events. And they are named as 1, 2, 3, 4, up to I think there are 25 such events. And actually, this is marked as a change in the oxygen isotope, 18, O18 isotope. So lower values of O18 will be lower temperature, higher values will be temperature. So it is a proxy for the temperature or the measurement which determines the temperature for this region. Okay. See, the recording is okay. So any doubts about the dance guard Oishkar events? Just informative.
Fine.
Okay. Nikita, any doubts?
No, sir.
Okay. So we will be reaching the final slide for today. Uh, there's a few questions regarding the AMOC and the Danskar, Oishkar events. So, okay, so what was the difference between warming and cooling in rates in DO events, Danskar, Oishkar events? So, rapid warming and milder cooling at those events, that is the characteristic features. And, okay, reasons for the temperature change in the Antarctic regions by the Laurentide ice shield and also North Atlantic Ocean, because the ice shields actually rapidly entered the Northern Atlantic Ocean. It stopped the AMOC circulation, not stop, actually weakened, make the circulation feeble or decreased. in that region. That's why the temperature transport of heat energy was not much in the northern uh, polar region or northern hemisphere. That's why we have experienced cold temperatures in this region. But it trapped more heating into the southern hemisphere. That's why the Antarctic region was warmed up. Now, why this is important? Because it can be related to the rapid increase in carbon dioxide and uh, change of the AMOC circulation. If there is rapid increase in carbon dioxide, there might be uh, insertion of fresh water into the northern pole, and that might decrease the AMOC circulation. Some models suggest that it will collapse in 200 years, very short time scale. So that is concerning. If it collapses, then there will be less heat transport in the northern hemisphere, and what will happen is the USA or European regions might experience drastically low temperatures instead of high temperatures. And it is counterintuitive because global warming refers to higher temperatures, but it also affects the AMO circulation, which controls the heat more efficiently. So at least for some period of time, that these regions can experience lower temperature compared to the normal. So it is not that in the global warming or climate change scenario only the temperatures will only increase. It can locally be decreased also. That's why it is of much concern. I mean, we are habituated to some climatic conditions. Changing that condition will anyways affect, be it warming, be it cooling, be it whatever the situation is. So it is best if we can keep the climate stable as it is. Any deviations from the stability will cause in the already adjusted things. Uh,
Increase in carbon dioxide can also increase the freshwater melting in the southern hemisphere also, right? Is it? I'm not sure about it, but
yes, carbon dioxide can increase the
temperature
fresh
in the
water in the
southern.
southern hemisphere. But
Cooling.
no, there is a difference between northern and southern hemisphere. So in the southern hemisphere, the temperatures are much lower compared to the northern hemisphere. So the predominant effect will be at the northern hemisphere. The southern hemisphere will also melt, but that will take longer time. So let's after 1,000 years or so that will be evident. But at least for the instantaneous time period, the northern hemisphere will melt fast because there is less ice in that region, and the average temperature of the northern hemisphere is higher than the average temperature I mean, at least in the Antarctic region, southern hemisphere. So that region is more vulnerable to the glacier melting and also the Atlantic circulation. That's why uh, that region will mostly contribute to the slowing down of the Atlantic meridional ocean circulation. But yes, you are correct. If there is melting in the southern hemisphere, then what will happen is it will also include a lot of fresh water into the southern hemisphere, and that will disrupt the circulation because in the southern hemisphere there is Atlantic deep water, and if that is warmed up, then uh, the amount of bottom deep water will also decrease. But I think that will happen after a long period of time, not instantly.
Okay, thank you.
Okay. Okay. So yeah, just we explain the cooling can happen in the northern Europe because of weakening of Atlantic meridional ocean circulation. Uh, the tropical heat transport will decrease, and that will lead to cooling. Though we are familiar with the global warming, we have a notion that it will warm everywhere due to global warming, but that is also a possible scenario in which we can experience exceptionally cold temperatures in the northern Europe or uh, northern America, this regions. So yeah, that was my last slide. So I will ask for any doubts for uh, this topic and as well as today's whole topic as well as any general doubts.
No, everything is fine.
Is there any doubts?
No, sir, it's fine.
Okay. So if it's fine, I will conclude today's session and we will meet next week. Okay.
Yes, sir.
Yes.
Thank you. Okay.